Okay, so this is our dynamics multimedia example problem. We modeled it after a tennis player hitting a ball at a wall and examining the loss in kinetic energy, while also taking into account the impulse momentum to find the final velocity when the ball hits the ground.
So the goal was to develop a multimedia problem to help students learn dynamics. Generally, the steps to do this, we identified the aspects of a good problem, did some research into what helps students learn, we developed and solved out a problem, and now we are giving the status to solve the problem.
Okay, so our problem statement, as I mentioned in the beginning, was modeled after a tennis player practicing for an upcoming tournament. The tennis player wanted to practice a particular shot against the practice wall and find out what the resulting angle and velocity after hitting the wall would be immediately after hitting the wall. And then also figuring out what the velocity is going to be right when it hits the ground. So there's multiple components in solving this problem. And as we go through it, you'll see how they all connect.
So as Kirsten said, that we're looking for the velocity immediately after the impacts, as well as the velocity of the ball immediately before it hit the ground. As you can see here on the upper left is the overall diagram of the problem description. On your right is the work energy diagram for 3 different positions, and below is the impulse momentum diagram.
Okay, so we started off solving the problem just by writing down our knowns. We know that the wall is smooth, and it's a key component to solving this problem, knowing that the wall is smooth so there won't be friction when the ball hits the wall. We're also given that 12% of the kinetic energy is going to be lost, and that's going to give us a big hint into finding the change in velocity. Also on this slide is our required findings. So we began just by breaking up the initial velocity into components, very basic trigonometry. We then used the principle of kinetic energy to first find, of course, the initial kinetic energy when the ball is coming at the wall. We know that after the impact, 12% of the kinetic energy is going to be lost. So we multiplied the initial kinetic energy by 0.88 to get the final kinetic energy. And we can also find out how much energy was lost in this process. Next, as you see, step 3, we use the equation of final kinetic energy to rearrange it, solve for the final velocity, that is the magnitude immediately after it hits the wall. Moving on, we had to draw a free body diagram to study the principle of impulse and momentum in this problem. As you can see, since the wall is smooth, aka no friction, there is going to be no force in the y direction. So when we write out our impulse momentum equation for the x direction, we are going to have a change in momentum due to an impulse, whereas in the y direction, there will be no change in the momentum. So we can easily see that the final velocity in the y direction will be the same as when the ball was approaching. Knowing this, we can then use the Pythagorean theorem of the final velocity magnitude squared equals what we don't know, which is the final velocity in the x direction squared plus the final velocity in the y direction squared. Solving this out, we were able to find that the final velocity is equal to 16.585 in the I hat direction and negative 8.767 in the j hat. Using the inverse tangent, we were able to find the magnitude as well as the direction. The next step was to use work and energy and the conservation of energy to find the final velocity when the ball hits the ground. This is a very simple energy problem. There was a little trick in there that the height we gave you for the ball hitting the wall was in feet. while the rest of our velocities were in meters per second. So you had to know to convert that to meters. The simple equation lets us find that the magnitude of the ball hitting the ground is 19.23 meters per second.
So through the research that we did, we concluded that there are multiple important components of a dynamics problem, clarity really being a top priority. The information given, what the student is solving for, and a diagram should all be made very clear. Having a clear problem allows the student to focus on the concepts, which has been proven to be most important in learning engineering skills. A multimedia example problem is an interactive way to involve the student in the problem and follow along to understand the concepts.
So now that we're done with the problem, we're going to talk about what we've learned. So in order to solve the problem, a student will have to have an understanding of multiplied dynamics principles. It was important to recognize how there was an impact in this problem. So therefore, it is implied that we use the impulse momentum theorem. Also, given in the problem statement, there was multiple positions given, and that usually signals off that you're going to apply work energy in some kind of way. This problem tests the student's understanding of these principles and also has an attempt to think outside the box a little bit to further their understanding in these concepts.
Thank you.